again, I'm back. I'm doing this same type of example, this mouse problem, so you can look back at the old lesson, but basically I figured it out. It was y equals 2 and 2 to the t. And some people are saying, no, you had a 6 there. And I agree, I did have a 6 there. But I want to know how to graph it, so instead of that, I'm going to make my time variable, which basically means that I want to catalog what the mouse population would look like at any time, at 0 months, at 1 month, at 2 months, at 3 months, etc. So what I'm going to do is I'm going to substitute in values. Now, you might as well just call the t and x when you're doing this. Y is your output, it's your answer, and t is your input. You could use any variable. You don't need t. You could use x if that makes more sense. But since we were working with time and y, I want to stay consistent with that. So let's get to the -1 later. So at 0 months, how many mice did I have? Well, how many mice did I have in my problem? You know, how many did I see? I saw 2. But let's go ahead and substitute that in. 2 to the power of 0. Anything to the power of 0 is 1. And then 1 times 2 is 2. 2 to the power of 1 is 2. And then 2 times this 2 is 4. 2 to the power of 2 is 4. And then 4 times this 2 is 8. 2 to the power of 3 is 8 times 2 is 16. It's actually pretty interesting. Whatever this number is in the parentheses will determine what it goes up by. So if this were a 3, each number would triple. That's, yeah, pretty much it. And if it's not, then kind of affects it a little bit differently. But that's from the point, so whatever the case. So looking at this number right now, this 2 right here. I'm sorry, not this 2, this -1. 2 to the -1 is 1 over 2. 1/2 times 2 is 1. What I basically want you to get from this, what I basically want you to understand, is that whatever the numbers are, they're getting bigger as you're plugging in higher t values, and they're getting smaller as you're plugging in lower t values. I want to show you what the picture of an exponential function looks like, though. And it depends, though. It depends what your rate is. It depends what your factor is. But this is basically the history of, not the history, but the summary of what an exponential function looks like. So here we go. At -1, it's 1. And this is your mouse population. Now I know we're not actually working with -1 months, but we're going to graph consistently with an exponential function. At 0, it's 2. At 1, it's 4. At 2, it's 8. Pardon, just a little off. And at 3, it's 16. And I only went up to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I'm going to go up to 16. Probably right about there. You can see what's happening. As more time passes by, that population is exploding. And that's basically what an exponential function does. So it goes up. It's not a line. It's like you bend the line. That's basically all an exponential function is. So it's kind of like a bent line, and it goes up really quickly. Now, what's interesting here, and this is what I was trying to debate about what I wanted to show you, as the numbers get smaller, -2, -4, -2, -3, -4, -5, -6, they get smaller and smaller and smaller. But they'll never actually reach 0. 2 to the -1000 will never be 0. It'll be really, really close to 0, but it'll never touch. What happens is this graph will get closer and closer to the x-axis, but not even touch it. And that's basically what an exponential function does. That's what's so fascinating, what's so interesting about it. Now this one will just continue going on and on forever, but it won't really do anything more than that. So, with that said, what we call this is, we call this an asymptote. Let me say that again. We call it an asymptote. Basically, an asymptote never really reaches a point, but it gets infinitely closer and closer and closer. And that's where we start talking about limits in calculus. But we're not talking about limits, and we're not talking about calculus yet. One aspect at a time. But I do want to mention something else that I think is pretty fascinating here, and we're going to go back to our old friends. Domain and range. And if you've been staying consistent with this, you'll figure out this a lot easier. If you haven't, then I'll remind you. Domain is the x values and range is the y values. So the x values are what inputs or what values I can substitute in all the time. Well, the graph is going to keep going this way and this way and this way forever. So my domain will be negative infinity, 2, and the graph will keep going this way and this way and this way forever. It will be sharp, but it'll still go, I can still keep substituting in x values as far as the eye can tell. So the domain is from negative infinity to infinity. Now the range is an interesting story. The range is the lowest value to the highest value. Now I'm telling you, it will never actually hit 0. So instead of a bracket, which I used before, which incorporates the number 0, it won't. It'll get really, 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 really close, but it'll never touch. And since it never touches 0, since that's an asymptote, a horizontal asymptote, and it's a horizontal asymptote because horizontal goes this way, my range goes from 0 to, and it'll go up and up and up and up and up and up forever, but it'll never touch. Well, it'll never reach its limit. So its limit that way is infinity with an open bracket. Something pretty interesting. When I get to domain and range for students, though, it's usually very difficult. I mean, some students grasp it really quickly and others take a little bit of time. So don't feel too bad. But you should practice domain and range consistently over and over and over again. Domain just means my x values, and range means my y values. So what I want to do next is exponential decay, see how that goes, and we'll talk about domain and range too, but we'll do a chart before we do that. With that said, hope this was helpful for exponential growth. Have a good day for now. Goodbye.